Today we're going to be going through the question 9 of the Maths Extension paper of Year 11. First of all, we'll start off with part A, part AI, which gives us this equation, 3px squared equals 2px. Now, the question tells us that p and q are rational, and we have to prove that the roots of this equation are also rational. Now, there are two ways you can do this question. The most common way is using the discriminant. So first of all, we'll move all of these three terms to the left side. 3px squared minus 2px minus 3qx plus 2q, that's equal to 0. Now, this all have x terms in it, so we will factorize the x out. 3px squared minus, oh my bad, minus 2p plus 3q x plus 2q, that's equal to 0. Now we would use the discriminant, so the discriminant is equal to negative 2p plus 3q whole squared minus 4ac. Now expanding this negative and the squared will just become positive, so we have 4p squared plus 9q squared plus 12pq minus 24pq. Now this here will just become negative, so 4p squared plus 9q squared minus 12pq. Now factorizing this, we would get 2p minus 3q whole squared. Now, since our discriminant is a square, perfect square, discriminant is going to be inside the square root in the quadratic equation, and this will cause it to cancel out. No more square roots in our equation. That means we have rational roots, assuming that p and q are rational, which is given in the question. Now this was the first method. The second method involves the same process in general, just factorizing the equation, and then proceeding from there, calculating the roots. So we have started with 3px squared equals 2px plus 3px minus 2p. Moving everything to the left side again, 3px squared minus 2px minus 3px plus 2p, that's equal to 0. So we will factorize p, we will treat this as two different binomials. Factoring px here, 3x minus 2. Factorizing negative p, we get 3x minus 2, that's equal to 0. 3x minus 2, px minus, oh no, px actually, this should actually be a q, sorry, and that means this would be a q, and that means this would be a q, and that's equal to 0, and that means our roots are going to be 2 on 3 and q on p. Now, personally, I use this method. This method is more straightforward, and we know that q and p are rational. Now, since they are rational, a rational number is defined as that number x equals a over b, where a and b are both rational numbers. We know that q and p are rational, as it's given to us in the question, meaning this root is also rational, and 2 and 3 we already know is rational because it's a fraction, meaning we have proved that the roots are rational. Now we will look at part II, which says what can be concluded about the number of roots if p is equal to 3q on 2. Now, this part of the question relies on the fact that we use the discriminant. Going to the discriminant, we have that the discriminant is equal to 2p minus 3q whole squared. So I'll bring that to the bottom. Discriminant equals, what was this, 2p minus 3q whole squared. Now, plugging in this value for p, we will get discriminant equals 3q minus 3q whole squared, and meaning the discriminant is equal to 0, and if our discriminant is equal to 0, meaning we have one real root. And that is part II done. We'll move on to part B, which says to sketch y equals x times absolute value of x minus 1. This question is pretty tricky, and what we have to do is focus on splitting up that absolute value so we can work it with it much more easily. Now, we will start off with, we'll make the assumption that x is greater than or equal to 0, meaning y is equal to x times, now this x here is going to remain positive as x is greater than 0, so we'll get x minus 1, and that's our function. And when x is less than 0, we will get x times negative x negative 1. Factorizing the negative 1 out, we will get negative x plus 1. Now, to graph this function, we would start at 1. Now, looking at 0, 1, use negative 1. Just looking at x is greater than 0, so this function right here, we will get the intercepts at 0 and 1, and it's upward facing parabola since the leading term is positive. It will look like this, and this function would be here. Then, looking at this function right here, when x is less than 0, it's a negative concave parabola which has the roots at negative 1 and 0, so it will look like this, and it will have a domain cut at 0 and the original function looking like this. And this would be our final graph. Now, looking at part C, we have two functions, f of x equals x squared plus kx minus 8, and g of x equals kx minus 4. Each of them having their domains of negative 2 to infinity, and this one is from 2 to infinity. Now, part I focuses on, and it also tells us that k is a positive constant, and our first I is write down in terms of k the range of g of x. Now, this question is pretty tricky, so we have to visualize this. If we draw the graph of g of x equals kx minus 4. Now, it's a linear line, and we know that the y-intercept is negative 4, so we will pick a negative 4 line here. And we will draw the line of x is equal to 2, as that's our domain restriction. This is x equals 2. Now, we see that whatever y value we draw, no matter what the gradient is, the gradient could be anything, and the value that's going to determine what the range is, what we will do is plug in x equals 2. Plugging in x equals 2 for any of this equation in the general form, we would get the point at which the line touches or intercepts with the x equals 2 graph. And this will tell us the point over here, these points. And these points all have one thing in common, where it is here where the graph will actually start to form, as this is where the domain of the graph continues. Now, as the graph starts here, x equals 2, what we do is we plug in x equals 2 into the equation. Plugging into the equation, for the general case, we are going to get a y value. Plugging in g of 2, we get 2k minus 4. Now, this is a y value that corresponds to these values right here. If I put them in another color, these values right here. Now, these values, this is where the graph starts. And the graph, we know that k is always positive, is only going to go up from there. And if it only goes up from there, that means this is the bottom restriction of our graph, the bottom y restriction. And this y value is given to us by this equation right here, where g of 2 equals 2k minus 4, and this 2k minus 4 is the lowest possible value of our function. So our range, if we look at the range here, will be y is greater than equal to 2k minus 4, and that is our range. Continuing to part II, it states find the if f of g of 3 equals 0, find k. Now finding k from here, we look at our two functions, which being f of g of 3, we know that is 3k minus 4, and plugging this into our x values in f of x. So we have 3k minus 4 whole squared plus k times 3k minus 4 minus 8 equals 0. Solving for this, we can expand this function, or we can try to factorize this function. Personally, to prevent any mistakes, I'll just factorize it. 9k squared minus plus 16 minus 24k plus 3k squared minus 4k minus 8 equals 0. So we have 12k squared minus 28k plus 8, and that is equal to 0. Now to factorizing 4 and dividing by 4, we would get 3k squared minus 7k plus 2, that's equal to 0. Now factorizing this, just a simple quadratic. This is off one factor, this is another factor. 3k minus 1, k minus 2, that's equal to 0. Solving for k, we get 1 on 3 and 2. And normally we would have to check for extraneous solutions, as k we know is given to be positive, and we know that k, and from the solution we see that k is positive, and therefore we have two solutions. And this is the final part of question 9 in the maths paper.